We are looking for Oriol Prat. No?
Okay.
Yeah? Okay. Like that? Okay. So I have an important announcement to say. We have 4 presentations now instead of 3, so it means we'll end at 6 and not a quarter to 6. So we have the first presenter now.
So Oriol Prat is presenting AI-based fish detection and classification at OBSEA Underwater Observatory.
Thank you, Simon.
Yes. When with that, can I pass?
With that you can pass slides.
Okay.
With that you can point if you want longer the button.
With that, what?
Yeah, if you hold the button, push the button, and keep it pushed. You see you can point something.
Okay. Okay, hello, good afternoon everyone. My name is Oriol Prat, and today I'm going to talk about our work, which is fish detection and classification at OBSEA. OBSEA is an underwater calvet observatory located at the northwest of the Mediterranean Sea, and is from 4 kilometers from the coast, 20 meters depth, and in there, we store multiparametric data such as temperature, salinity, pressure, currents, waves, and also we have images since 2011, which is potential information to do fish abundance and study behavioral studies of these marine species. There are many photos taken in that place, and let's talk about the project. We are from the use case 3 of the imaging project, and the main objectives is publish real-time data from these species, and also monitor the ecosystems using these underwater images with these 2 mainly target users, and using AI models, in this case YOLO V8 and YOLO V9. Here is a workflow. In the first step, we have the acquisition of the images, and then we store this in an intern server to then use this imaging platform for doing the inference once the model has been trained. And then we can store and use image tools like Grafana, which is useful, and we are going to see then. This is an example of an image with the detections with this bounding box of each fish classification. Traditionally, the way to monitor these marine ecosystems was extremely time-consuming. That is, marine scientists have to count every fish in every single image, and as you can imagine, this took a lot of time. And then store in some tool like Excel or something like that to finally get this abundance time series. And these have so many inconveniences that you can see in red. But nowadays, instead of counting manually, the idea is to apply these algorithms, which in this case we use YOLO, you only look once. And then we can train with so many configurations. Here, there are different species that you can take in account, different YOLO and not only YOLO models, different size of the model, different learning rates, using data augmentation or not, playing also with the image size. And then we store these predictions, this inference, and not only the photo, but also the data in this bounding box in a XML or TXT file, to finally get this abundance time series to take an example. So let's do science and not count fish to have an idea for comparison with 50K image analyzed. A scientist took 1 year more or less to count these fishes, and with these AI models took 12 hours more or less. So up to today we have semi-automatic labeling methods because the first steps is to collect these pictures, then we run the inference with the model pre-trained in these new images, and if they're not exactly that we want, we drop these predictions in some software like Label Image. In there, we can adjust manually if the detection is not really as we want, and then we can train with this new data set, and we can do this loop infinity and improve the model. This is the species that we have up today, 21 species, and we can see the total images, and these numbers are the instance, the number of content fishes in the total data set. Up today, well, not today, but in November, we have these results, which is mean average precision, which is quite good. 12 classes or species, and this amount of images and annotations. Up today, we have more precision, but the most important thing is that we have more classes, which is a great improvement. And the idea is in the diagonal, the score is better if it's close to 1. And we are going to talk about this chromis back later. So we have been doing the data preparation at least 80% because we have to wait 1 year to have the seasonality covered. And the model training, which in this case, we found that the best configuration is with these 21 species, with YOLO BE9, and with the extended version, with the minimum, with the lowest learning rate, using also the image size 2K in this case, and data augmentation, which is different component of the photos, like flip, right, left, grayscale, and a lot of configurations. We also we integrate this model in MLflow, which is a platform that you can see graphs and compare with different models trained, and also with ClearML, in which we can see also the metrics for the computer, like GPU. Up to date, we publish the data set that we are using in Zenodo. All of you can see it, and we have also real-time streaming on YouTube. Let's see some results, if it works. Nice. This is one of the cameras that we have. And this is a video, so we run the inference frame per frame. This chromis, there are two colors because we say that there are two classes, chromis back, which is not a perfect detection, but we have more detections in total. Let's see another video from another camera. This is an inference from the past August. In there are many different species in there. Okay, so the next steps for our group is move all this to production. Before I talk about Grafana, Grafana is a tool in where you can visualize, for example, in this time series, we have chromis and dentex, which we think that this prey and predator, and we can see all the predictions that we have from the past, and the images without the bounding box and with the bounding box. So the idea is move all this to production to have, once the images come from the camera, we can publish this in Zenodo or something. And then we are working also with alarm system with key species, for example, rayas or something that was interest for the biologist. We want to try also oriented bounding box. Maybe we can have more information about the fish moving, and the scientific exploration in further research. We are working also with predator and prey interactions, in this case chromis and dentex, and link that with an ecological models, and also have correlation with environmental data, that we can see that there are many correlation with solar irradiance or with temperature, salinity, and so on. So thank you for all. I hope you was interesting, and thank you.
Not yet? No?
Thanks a lot. A very interesting presentation. I think the movie is a very nice illustration also of how the model is working. Very cool to see. Are you utilizing, it seems to be a lot of information to disambiguate the classification in following the fish from one frame to the next. Is that utilized in the final classification of fish? So you could see the fish classification changing from one frame, yeah, right? Yeah. So, but that's information that you also have available in the classification, the vicinity between frames and things like that. So is that used in fish classification?
I think that you are talking about, which is another way to do it with tracking. Because in this way you don't lose information frame per frame, but if the fish goes disappear from the camera and then the same fish comes another time in the camera, you are counting like two species difference. I don't know if this is the. I mean, you are talking about the information loss in frame per frame.
Yeah, I was just thinking about using the information from neighboring frames in disambiguating, right? Because it seems that it's more ambiguous, the classification from some angles than from others. But yeah, just an open question. It's thank you.
Thank you. Very nice presentation and a really wonderful video. My question is, for your images, when you annotate them with the species and the number of species, I guess, yeah. What do you use a standard? How do you do that? And how do you, what do you feed your AI algorithm with?
What do you feed?
Your AI, your artificial intelligence algorithm,
yeah.
you feed it with images, but with annotations as well, I guess,
exactly.
per image. So what are these annotations? Are these XML, the one that you showed?
Well, in the YOLO information, the idea is with TXT, but we lost information and we use XML because in there you have the name of the species and the bounding box and so we have the image with the same name as the XML, and with that we can train because there are the image size, the pixels, and you can use, where exactly is the bounding box, and there are many different ways to do it, like with the corners, with the center, and width and height, but I don't know if this is the question.
Yeah, this is the question.
Okay.
And like maybe you could be looking at different standards like JSON, which is a bit faster than XML,
exactly.
and also using some ontologies to describe your annotations.
Exactly.
And then the other thing that I was thinking is, who does the validation of counting the fish after, you know, your AI algorithm said, okay, this image has this many fish and of this species, who does the validation if this is correct or not?
Exactly.
It's a very long...
Exactly. There are many, we have a specialist in taxonomy or biologists in our group. So the ground truth is this person. I mean, and then imagine that you have more or less 20% of the data set, you have to label it and for train. So yes, there are an human error.
Yeah.
If, for example, this day I have the bad day and I see, yes, there are human error. Exactly.
Okay, thank you very much. It's very interesting.
Last question, Sisi.
Very short one, just from curiosity mostly. Aren't some characteristics during classifications like fish length or height that could help you to not to double count the abundance of fishes?
Double count?
Double count, yes.
Well, imagine, look, this image, for example, is easy to not found. If the fish is in lateral position, like that, is easy to detect. But if the fish, for example, is in front, it is not easy because there are the model thinks that is a dentex, maybe it's Oriola, maybe it's another. So I don't really understand what you say, that double counting. To another picture. Yes, exactly. This is our problem. If you want to do abundance time series or something like that, because there are no tracking in there, because it's not like orcas that have a specific feature in the. No, it's, I mean, fishes, super similar. See, the tracking, we are working with that because if the camera, if the fish goes from another way and then come back to the camera, the algorithm is taking 2 times the same fish. This happens.
I'm sorry, we have to.
We are told.
All right.
Thank you.
Thank you very much. Well, let's move to the next talk.